Okay, as promised, we're going to continue on with 4.1, finding extrema of functions using critical values. But now we're going to be limiting those functions artificially by using an interval, okay? So we're going to be dealing with this on a closed interval. And if you don't remember what closed interval means, it basically means an interval like 0 to 4 where you have it inclusive, okay? So that is on the closed interval right there. Now I want to find the extrema on this closed interval. Well, the first couple of steps are identical to what we did when we were doing it on the implied domain. We just do 3x squared minus 12. Then, since this is a polynomial, we know that we're just looking for x squared minus 4. We're just looking for the zeros, not the undefined points, but the zeros of the derivative function. Fight the urge to push the 4 to the other side, because half of you will forget the positive and the negative too. Okay? Now you know what this looks like, okay? You know what this looks like, and you know that positive 2 is going to be a minimum on that interval, most likely, okay? But here's the great thing. When you're dealing with it on a closed interval, okay, you don't have to do the sign chart. Because if I basically go to the new equation and I say, well, let's go x cubed minus 12x, okay, and let's zoom out, okay? What happens here is if I'm dealing with 0 to 4, well, do I care about these values over here? No, and I don't care about these values over here either. What I have here is I have basically, at 0, there's a point, okay? At 2, there's obviously a minimum, it's way down there, and at 4, there's going to be a point. Well, here's the thing. Instead of doing a sign chart, just basically what you need to do is you need to evaluate the function at any critical value. So f of 2 is obviously 2 cubed minus 12 times 2, and that winds up being 8 minus 24, or negative 16. And then you just need to compare the critical values with the function values at the endpoints. F of 0 is 0, and f of 4 is, well, here's the thing. 64 is 4 cubed, minus 12 times 4 is 48. That winds up being positive 16. Well, here's the thing. You know that the only way that a point is going to be greater or less than one of the endpoints is because it's a critical point. So basically evaluate basically take the derivative, find any critical points, and then you evaluate the endpoints and any critical point that happens on that interval. Then you go, well, 0, negative 16, positive 16. This is the smallest, so that's the minimum on that particular interval. This is the greatest, so that's the maximum on that particular interval. Done. I mean, that's literally it, okay? So, let's go ahead and move on to another example, okay? This is f of x is equal to 3x to the 2/3 minus 2x from negative 1 to 1, okay? And I want to evaluate and find the extrema on that closed interval. Okay, well, let's go ahead. That's 2x to the negative 1/3 minus 2, okay, which can be rewritten as 2 over the cube root of x minus 2. Okay, well, I can already go ahead and say, well, there's going to be a critical value at x is equal to 0, because that is a point at which the derivative is undefined, but the original function is defined, okay? But I also know that, this is going to wind up being 2 minus 2 cube root of x, all of that over the cube root of x. I happen to know that it's also going to be at x is equal to 1, because at x is equal to 1, the numerator is equal to 0. So I have critical values at 0 and 1. Well, here's the thing. I was already going to evaluate 1 because it's the endpoint. So I don't really have to worry about that because of the interval. So all I really have to do is evaluate f of -1, f of 0, and f of 1, and then just compare them. Well, it might be a good idea, you know, if this helps with your thinking. You can go ahead and just, you know, factor it out if that helps. If it doesn't, then just don't worry about it, okay? So if I plug in a -1 into here, it's going to be, remember that anytime you have a fractional exponent, if it has a even number in the numerator, then that's an even, that's an even power, and therefore a -1 is going to become +1 in that particular instance. So it becomes 3 plus 2, or 5. At 0, obviously it's 0. And at 1, it's going to be 3 minus 2, or 1. Okay, well, which one is going to be the maximum? Well, this is obviously going to be the maximum at -1, 5. And this is obviously going to be the minimum at 0, 0. And if you're curious about that, we can go ahead and go over to Grapher and actually look at it. Let's go ahead and get a new equation. We'll sort of cancel that one out, or just blank it out. And so we're going to have 3, and so I seem to remember something about this. I think I have to do it in pieces. 1/3 minus 2x. No, it's minus 2x. I think that's how I have to do it in Grapher. And basically that right there is my graph. Okay, so from -1 to 1, and we can zoom in to actually show -1 to 1. At -1, it's 5. See that right there? That ordered pair right there. At 0, it's 0. And at 1, it's 1. So I've actually evaluated that rather well in terms of my analytic work. I've gotten the maximum on the closed interval at -1, 5. I've gotten the minimum at 0, 0. This is neither, because that output at +1 is between 0 and 5. Okay? Now, let's go ahead and do a third one. This one probably will not be quite as agreeable to all of you because it's going to involve absolute value. But since your teacher likes absolute value, we're going to go ahead and deal with it. And I'm going to remind you how in the world to think about absolute value. Okay? Now, absolute value is not difficult. Absolute value just happens to be one of those things that we never think about. Okay? And therefore, this winds up being, remember that what you want to do is you want to change it like that. Now remember what the parent function of absolute value actually looks like, okay? You know that it basically is a big V, okay? And this one is basically just transformed, right? It's to the right 3, an x-axis reflection, and then moved up 3, okay? So there's no stretch, it's just an x-axis reflection, and so we actually should be able with relative ease to go ahead and graph this particular function. So let's go ahead and do that really quickly. We haven't done that in quite some time with an absolute value function, but I see no reason why we can't do that very, very quickly. Okay, now let me go ahead and remind you this is y is equal to negative absolute value of x minus 3 plus 3. The vertex is going to be at 3, 3. So the vertex is there, and it goes down from there, okay? Goes down from there. And there's no stretch, so there's going to be a slope of 1 and -1, okay? And if you're interested on the interval from -1 to 5, -1 starts here, 5 is there. So just based upon your knowledge of the graph, that's -1, that's 5. Just based upon your knowledge of the graph, there's your minimum, there's your maximum, and that's neither right there. Okay, well, basically what needs to happen here, because it's a absolute value function, is probably the best way to deal with this is actually just to pull it apart into its probably the best way to do this is just to pull it apart into its piecewise. Okay, and so here's how I would do it. I would just say, well, I recognize this function, the left hand side of it, that's just x, where x is between -1 and 3, and then that winds up being -x plus 6 for x between 3 and 5. Okay? And from there, you can basically determine that the slope, the derivative, is undefined at this particular point right here. Because remember, the slope is, the derivative is a limit, right? And the limit from the left and the limit from the right are not going to be the same, and therefore the derivative does not exist there. And then you would just evaluate it at the endpoints, and of course at that vertex point right there, coming to the conclusion that -1, 1 is the minimum, and 3, 3 is the maximum. Now, the funny thing is that if you remember the graph, all of this winds up being really, really easy. The hardest part is pulling it apart into a piecewise function. But let's go ahead and do one more, since we actually have the time. I think we're coming up on about 12 minutes right here. So if we have y is equal to x squared over x squared plus 3, and we're going to go from -1 to 1, what do we notice about that new function? Well, we should recognize the fact that, we know what 1 over x squared plus 3 looks like, okay? That's the Witch of Agnesi, right? Or it's a transformation on the Witch of Agnesi. Basically just kind of looks like, it just kind of does this number. It goes, whoop, like that, okay? And of course, we saw that when it was 1 over x squared plus 1, and then we put an x on top and it became the serpentine function in a previous one, right? Well, this is still even in the denominator. What happens when I have another even in the numerator? Well, it stays even, right? So this is an even function, so it should have symmetry about the y-axis. Well, I also have a closed interval, which is symmetric about the y-axis. So it should be no problem for me to surmise that -1 plugged in here is going to be identical to 1 plugged in here. It's going to be -1, 1/4, and 1, 1/4. The question is what happens in the middle, and it should happen right in the middle, but we need to go ahead and confirm that using our calculus. So let's go ahead and take the derivative. Now, I could change that function, right? I could change that into x squared plus 3 minus 3, okay? And then, of course, that winds up being 1 minus 3 x squared plus 3 to the -1. So I could take the derivative by the chain rule from here, but this is really not that difficult in terms of the quotient rule, and everybody needs practice with the quotient rule anyway. So let's go ahead and do that. The bottom times the derivative of the top minus the top times the derivative of the bottom, okay, all of that over the bottom squared. Now when this distributes, you're going to get 2x cubed and a -2x cubed. Those are obviously going to cancel out, and the only thing that's going to be left is going to be a linear term, which means, predictably, that your critical value is x is equal to 0, okay? And the only thing that happens at x is equal to 0 is you get, when you plug it back in, 0, okay? So you know that, well, we didn't do it in terms of f, we did it in terms of y. Y of -1 is 1/4, y of 0 is 0, and y of 1 is 1/4. So your maximum is actually shared by the endpoints, and your minimum is that one right there. Now, just really quickly, let's go ahead and look at that graph. Let's go x squared, and I think that's probably the best way to do it. X squared plus 3. And if we zoom in just a little bit, we wind up seeing that from negative 1 to 1. See, at 1, it's 1, negative 1, it's 1/4. At 0, it's 0. And at 1 over here, it's at 1/4 again. Okay? Which makes sense because that winds up being a Witch-of-Agnesi times a parabola. Okay, and of course the zeroness of the parabola is going to drive that that initial y-axis, that y-intercept of the Witch-Agnesi down back to the origin. I hope that that's helpful in terms of finding extrema on an interval. In the next video, we're going to get into examples that are a little bit nastier, you know, transcendental functions, trig, exponential, stuff like that. But I wanted to go ahead and do, you know, basically really bare bones ones in this particular video, so that we got a grasp of extrema on a closed interval, and we'll get into a few nasty examples in the next video.